And finally, our last example, looking at how we apply Newton's laws to circular motion. We're going to look at now how a car makes a turn. When cars go around a curve, there must be a net force towards the center of the circle, of which that curve is an arc. If the road is flat, that force is, of course, supplied by friction. So friction is a pretty important force. It allows us to speed up, slow down, and turn. If the frictional force is insufficient, the car will tend to move nearly in a straight line, which is indicated by those skid marks that you see in the diagram to the right. So the car is attempting to make that turn. First thing to notice is that you can see how they sort of increase the value of R. So if they start on the outside of the turn and sort of cut into that corner, the inside portion of that turn, you can see that they're actually increasing the value of R. Now, if centripetal acceleration is v squared over r, if I can make r bigger, I reduce the acceleration, and if I reduce the acceleration, I need less force. So we can make that turn more easily by making r as great as possible. Now you can see if they don't have enough frictional force pointed inward, they will end up moving in a straight line, as that diagram shows. Now, as long as the tires don't slip, that friction would be static friction. If the tires do slick, then the friction will go to kinetic, which is bad for a couple of reasons. First thing is that the kinetic frictional force is smaller than the static frictional force. I should change this to say smaller than the maximum static frictional force. So maximum static friction is always greater than kinetic friction. Okay. Now that might help if we remember looking at this particular graph. If I were to draw how the frictional force is related to the applied force, we looked at a graph that looks something like this. So this region here, this region was called the static region. Okay, so this was static friction. And this region here we called the kinetic region. Okay, and we can see clearly that the kinetic frictional force, F sub k, is always less than Fs max. Okay, so that graph sort of helps explain why it's bad if we have kinetic friction. Trying to make that turn. Now the other thing is that static frictional force can point in any direction, including the center of the circle. And that's what we need in order for us to make the turn, is that we need the tires to sort of push outward on the ground so the ground can push inward on the car. Kinetic frictional force, though, only opposes motion. It cannot push inward. Kinetic friction cannot be a centripetal force. It cannot point inward. So if we do not have static frictional force acting on our car, then all we can do is simply slow down. We cannot make that turn. It makes it very difficult to regain control and to continue around the curve if we start to slip. Now let's look at, I'm going to save that slide for another time. Let's look at applying Newton's second law to curved motion for a car. So let's try this, this example problem. A car, mass 1,550 kilograms, rounds a turn on a level road. The car is going to complete the turn without slipping. What is the maximum speed the car can have to complete the turn? Let's assume the coefficient of static friction is 0.75, so that's pretty common for rubber on dry concrete. And let's take the radius of the turn to be 85 meters, so perhaps a radius for like an off-ramp or an on-ramp. Let's go ahead and draw a little section of road here that's showing a curve. So let's say that I have that car at this point, right at that point in the turn, and let's see, it's traveling this way. Call that V sub tangential, and it's trying to move along an arc that's sort of described by this path. And just to make this as simple as possible, let's assume that that's a nice little perfect circle. It's got a radius. That circle's radius r, we said, was 85 meters. And we're interested in finding the maximum speed that they can have without slipping. Now, if that's the tangential velocity, let's make sure we understand the orientation of the acceleration vector. The acceleration, remember, we call that centripetal. That's pointed inward. We see the velocity and acceleration are perpendicular, as we would expect for circular motion. Now I want to draw an FBD for that. So these are velocity and acceleration vectors. Those are not forces. Let's go ahead and draw that FBD. Right here, let's look at that car from the rear. So let's go ahead and draw that car. Let's make it so it's easily understood to be the rear portion of that car. So we're looking at it from behind. It's making that turn. Let's see if we can't draw what those forces would look like. Now we know the weight would be pointed downward. We know the normal force would be pointed upward. And clearly at this stage in the game, we should know that these two forces are balanced, equal but opposite. And let's see, that would be the FBD for the car traveling on a straight road without turning or anything like that. They'd just be traveling like so. But we're actually accelerating. We're accelerating towards the center here. So we need to be able to account for the forces that are acting. There's got to be another one pointed this way. It's the force that's producing the centripetal acceleration. So let's go ahead and draw that here. That force would be inward, pointed towards the center this way. We might call it generically the centripetal force, but in reality we know that that force is static friction. Okay, so it's the force that the rubber exerts on the road. It's the force that the road exerts on the rubber. As long as there's no relative motion between those two surfaces, that would be static friction. Now, because we're looking for the maximum speed, I'm going to make that be the maximum static frictional force. It's the speed at which we just would start to slip. If I went any faster, it would be right at that particular point where I'm getting maximum static frictional force. So I'm looking for that particular speed. Now, that's my FBD. Let's make sure that this is clear. That's a rear view, so I'm looking at it from behind. When I go to determine what that maximum speed is, I, of course, use nothing other than Newton's second law for centripetal motion. I see that there's only one inward force. There's only one force that's pointed along the center line, and that is, of course, none other than my Fs max. So let's go ahead and replace that. I'm looking for the speed, so let's use this version for the acceleration. Now I see that, let's see, I'm looking at my equation sheet and I see that the static frictional force, Fs max, is defined as the ratio, as mu sub s times the normal force. Well, in this case here, let's go ahead and write that, mu sub s times n. In this case here, I see that n and w are the exact same value. So let's go ahead and replace n with the equation for weight. Now that doesn't always happen, but in this case we can do that. So mu sub s times mg is equal to mv tangential squared over r. That makes it really nice. I see that the mass of that car ends up reducing out. It's a pretty important phenomenon related to moving through a circle. It doesn't matter whether or not the car is a really massive car or a very lightweight car. It doesn't matter. The masses end up reducing out in that equation, which means that the speed that we can make that turn without slipping is independent of the mass. Let's go ahead and continue that by solving that equation for Vt. Multiply both sides by r, take the square root, and I would see that the speed at which I can make that turn is a function only of these three things, mu sub s, g, and r. We can go ahead and plug those numbers in for this particular problem just to be able to get a numerical value, 0.75 times 9.8 meters per second squared times 85 meters, and we get in the neighborhood of 25 meters per second, which is about 55 miles per hour, maybe 56 miles per hour. So we said that this problem might be something like going on an off or an on-ramp. Typically the speed limit on an off or on-ramp is maybe 25, 30 miles per hour at best. You could probably, if this were that problem, you could go up to 50, 55 miles per hour. Start going any faster than that, you're going to end up sliding right out of that turn.